Welcome to this lecture series in linear algebra. We will continue with our short excursion on permutations, which we require to define the notion of the determinant in the most general setting. So let's recall what we need for this lecture. We discussed what is a cycle. So a permutation is called a cycle. A permutation sigma on a finite set X, let's say, is called a cycle if the digraph of sigma witnesses exactly one non-trivial graph theoretic cycle. Think something like that. So the identity permutation is something that I'm not calling a cycle, although one could call it a zero cycle if one likes. Perhaps that would be a good convention to not write exceptional statements in theorems. But since I have not taken that convention, unfortunately, when I say a cycle, I will mean a K cycle, meaning a permutation whose digraph witnesses exactly one graph theoretic cycle of length k, where k is at least 2, because there is no such thing. We are not going to talk about cycles of length 1. They are loops, so we will not allow them. So anyway, we defined and discussed what cycles were, and then most importantly, we discussed that the phenomena of cycle decomposition. Now, this does not have to be confused with the cycle decomposition theorem of linear algebra, which says that if you have an endomorphism on any vector, finite dimensional vector space V, then you can write the vector space as the direct sum of cyclic subspaces. No, this has nothing to do with that. It just says that if sigma is a permutation on a finite set X, and assume that sigma is not the identity and it is also not a cycle, then you can write sigma as the composite of disjoint cycles. This composite may involve more than 2 permutations, but you can express sigma as the composite of disjoint cycles, which means what? Which means that the cycles appearing in this decomposition will have disjoint support, so to say. So if so you call 2 permutations sigma and tau as disjoint if something is fixed by if something is moved by sigma, then that is necessarily fixed by tau, and if something is moved by tau, then that is necessarily fixed by sigma. So that is when you call sigma and tau as disjoint. Okay, so this is just so much for the recap. You can go back to the video if there is something that is bothering you. And now let us proceed. So the topic of this lecture is transpositions, and transpositions are very easy to define. A permutation is called a transposition if it is a 2 cycle. So in this example, we have a permutation of a set of 5 elements, and the digraph is this. So this is a 2 cycle, and that is the definition of a transposition. Let me write it down. X be a finite set, sigma be a permutation on X. We say sigma is a transposition if sigma is a 2 cycle. Alright, so somehow 2 cycles have a special place in this theory. Let's take an example computation. So here we have a transposition of the set of 5 elements, and this is another transposition of the set of 5 elements, and we are composing them. So first you apply the first one and then the second one, and we want to find out what is the result. Something interesting is going to happen. So the first transposition fixes 1, 2, and 5 and switches 3 and 4, and the second one fixes 1, 4, and 5 and switches 2 and 3. So the vertex 3 is moved by both of them, but the other one is different. And yeah, before I even come to that example, just note that if tau is a transposition, then tau composed with tau is the identity map. So this is a small exercise, you must do it. Okay, now coming back to the example, we want to find out what is this composite. Alright, so let's start with 1. The point 1, first you're feeding 1 to this permutation. Well, 1 is fixed, so the output of this guy is 1. So 1 will be fed to the subsequent person, and 1 is fixed by the subsequent one also. So 1 will be fixed in the composite. We are just using the definition of the composite of 2 maps. So this is not moved by the composite permutation. What about 2? 2 is fixed by the first person, but 2 is moved by the second one. So if you feed 2 to this guy, it will output 2 and send it to the second guy, but the second guy takes 2 and outputs 3. So 2 is moved to 3 under this. Under the composite, 2 moves to 3. Alright, what about 3? What happens to 3? So you feed 3 to this guy, what does it do? It takes 3 and outputs 4 and sends 4 to as an input to the second one, but 4 is fixed by the second one. So the output of 3, when you feed 3 to this composite, you get 4. So 3 moves to 4. Okay, maybe I should have just drawn a single straight line. Yeah. And now, what about 4? 4 moves to 3 and 3 moves to 2. So 4 goes to 2. And what about 5? 5 is fixed by the first one as well as the second one, so 5 remains where it was. So something very interesting has happened. The composition of these two transpositions has become a 3-cycle, right? That's very nice. So it's a nice computation, but this is a general phenomena, and that is what we are going to discuss. So let's compute the composition of 3 transpositions. All of them have this one in common, in the sense that all of the 3 transpositions move 1 to something. The first one switches 1 and 2, the second one switches 1 and 3, and the third one switches 1 and 4. What is the outcome? Of course, you should pause the video and find this out yourself, but I will do it in full detail, and then I will leave you with an exercise. So let's do it. What about the first one? The point 1 first moves to 2. 2 remains where it was in the second one, and 2 remains where it was in the third one. So 1 moves to 2. Make sure you follow this. What about 2? 2 moves to 1, 1 moves to 3, and 3 remains fixed. So 2 moves to 3. What about 3? 3 remains fixed, then 3 is moved to 1, and then 1 is moved to 4. So 3 goes to 4. And lastly, what about 4? Well, not lastly, but anyway, 4 is fixed here, 4 is again fixed here, but 4 moves to 1. So we get 1 back. And what about 5? Well, 5 is fixed by all of them, so it will be fixed in the composite also. So the composite of these 3 transpositions is a 4-cycle now. In the previous example, it was a 2-cycle. It was a 3-cycle when we composed 2 transpositions which had one kind of node in common. Now we have 3 transpositions which have a node in common, and the other counterparts are all different. So we get a 3-cycle, we get a 4-cycle. And I leave you with an exercise here that if you compute the composite of these 4 transpositions, all of them move 1 to something, but whatever they move it to is different in all the 3 things. And if you compute this out, what you will find is that you get a 5-cycle as a result, and I think it will just turn out to be 1, 2, 3, 4, 5. Oops. What have I done? Yeah, 1, 2, 3, 4, 5. The 5th one is here. So 1, 2, 3, 4, 5, and then back. So this is what you should get. All right, so if you just play around with this, it already suggests a theorem, if you like. Here what happens, you can write this 4-cycle as the composite of 3 transpositions. You can write a 5-cycle, whatever is the result of it is going to be a 5-cycle, which we see can be written as the composite of 4 different transpositions. And any k-cycle can be written as the composite of k-1 transpositions. And I'm not going to prove it formally, but I'll state it. You can prove it if you like. It's just a simple induction. So fix any k-cycle, meaning fix a permutation of a finite set x, which is a k-cycle. Then you can write the permutation as the composite of k-1 transpositions. This we observed in a few examples, and it is very easy to prove, so I don't want to write a formal proof of it. As a corollary, fix any finite set. Every permutation of sigma, regardless of whether it is a cycle or not, can be written as the composite of some number of transpositions. Why is that true? Well, first of all, suppose sigma is the identity. Then pick any transposition and write sigma as the transposition composed with itself. You will get the identity map. Fine. Now if sigma is a cycle, suppose a k-cycle, then the above theorem does the job. And lastly, if sigma is some other permutation, which is neither identity nor a cycle, first you use cycle decomposition of sigma. So you write sigma as the composite of various cycles, disjoint, and now write every cycle as the composite of various transpositions. So every permutation can be written as the composite of transpositions suitably chosen. So that's very interesting. Transpositions generate all permutations. Even though one transposition is kind of a very measly thing, it just switches switches two things. But together, the set of all transpositions generate the entire set of permutations. In fact, you don't even need all transpositions. A small number of them suffice. But anyway, we don't need that. So just make sure you understand this corollary. And we will, after this, discuss permutations in one more lecture. We want to talk about sign of a permutation. And then we can move to determinants. Alright, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.